And now what I'm trying to do, I'm solving part 2, right? I want to get an expression that doesn't have any more integrals in it, okay? So therefore, I say, IM. What's it equal to? Well, this is my recurrence relation, so I start to write it, but then I don't write the next bit because it's an integral, right? So I don't want any integrals in this expression. So therefore, I say, well, that's okay, because I know what I of n minus 1 is. It's this, right? So then I begin to write this. Actually, I'll put the minus sign there. And then I'm about to write this part. But I don't want to write it because it's an integral. So I say, that's okay, I know what that looks like too. So I write the next part. 2, isn't it? Yep. You see what I've done here? Now there's my pattern. And then I say, well, this is just going to keep going. This is going to keep on multiplying. ... At some point, he'll get to here. Right? So then I say, okay, well, I can actually finish this ladder and then get off this thing, right? So this is minus, no, here I am, minus 4 over 2. Like that, yeah? Times minus 3 over 2, times minus 2 over 2, yep. And then the last term is times minus a quarter. Let me stop and make sure that I'm on the right page. Excellent. Okay. Now, what on earth do I do with this thing? Well, the good news is I've kind of gotten what I wanted, right? Look, it's a statement for I of n, and there are no integrals. Look, Ma, no integrals. I got rid of all of them, right? I did it n times. I admit I took a bit of a shortcut in there, but we have the pattern established, and that's all I'm after, okay? Now, I'm going to do one thing before I actually close this up into a nice tight bundle, before I can actually finish this off. Have a look. How do I get from one term to the next in this product? Well, for starters, every single term has a common factor. Did you notice that? There's a minus 1 on the numerator, and then there's a 2 on the denominator. So there's a factor of negative a half every single time. If you just take that guy out, because he happens every time, what's left? N? N minus 1? N minus 2? Okay, so this is an AP, isn't it? But I will point out, it's not the APs that we'll be dealing with, because we would usually think about a series, which is this plus this, plus this, plus this. That's an arithmetic series. We're dealing with a product here, aren't we? Okay, so there's that to one side.
All right.
So you've got n minus 1, n minus 2. Now the pattern continues here, almost. Look, you got 4, then 3, then 2, and then you're like, uh-oh. What should be here? What's missing at that spot? Right there. There's something missing. What's the next term you would expect? If I didn't show you this last thing, what would you expect? You'd expect minus 1 over 2.
But it's there.
Now, because it's not there, but I want it to be there so that it finishes off, it ties my entire bunch of terms in a nice neat bow, I'm going to generate this and pull it out of there.
Yeah,
Okay? I'm just going to do it. So here, watch. Right? Wrong color. Yeah, he is there. Okay. So I'm going to write, this is just going to stay the same. Minus, I meant the minus outside, times, oh my, this, times this, times ... Okay, where am I going to end up? Okay, well, I've got minus 4 over 2, minus 3 over 2, minus 2 over 2, and then I want this guy, right? I want that guy. So it's almost like completing the square, except not at all, right? I've got this left over, so to make sure that this bunch of terms is actually equivalent to what it came from, I need to multiply finally by a half. 1 lonely a half. And we should expect that he's a bit of a weirdo, right? Because he came from somewhere else, right? He came from actually evaluating a real integral, okay? So even though he doesn't fit in the pattern, he's kind of not meant to fit in the pattern because we got him somewhere else. Okay, now we're ready to really tie this whole thing up. Remember I told you that every single one of these terms has a common factor of negative a half, yeah? Negative a half. Well, how many of those negative halves are there? And the answer is, if I start counting from here, there's the first one. There's 1, 2, 3, 4, ... n minus 1, n minus 2, sorry, n minus 1, there are n terms in this. I keep on wanting to say sequence or series, but it's neither of those. There are n terms in this product. Okay, so therefore, there are n lots of negative a half. Yeah. Now there's the first thing. Then you told me if I take those guys out, all you're left with is n times n minus 1 times n minus 2 times all the way down to times 3 times 2 times 1. We have a name for this, right? This is n factorial. Bam! Right? So because of this product, this is what appears. Okay? Now that means these two things together, they take care of all of those terms. Right? All the parts from the recurrence relation. And then you've got this lonely guy, right? Now because he doesn't have a negative sign on him, you don't want to confuse him with here. So I'm just going to write that. Okay? Whoa. Look at that. Look at what we just folded this enormous, insoluble thing down into. Okay? So, we got the recurrence relation. Then we got out of the recurrence relation. This is not a recurrence relation anymore. Okay? Because it's not recursive. It doesn't depend on any I, any type of I, n minus 1, n minus 2, whatever. It's just in terms of n. That's amazing. Right? So, the last question, I'm even going to fit it here because it's got so little to it, right? The last question is this. 0 to 1 of x, sorry, there's no n there. It's log x to the 5. Well, that's the one I gave you. Okay? So what is this in terms of I? Which I is this? It's I5. Right? So then you say, oh, okay, this is, according to this, it's a half times minus 1 2. Now, the beauty of this, because of how far we've gone, you don't even need a calculator for this one. There's 5, there's n, and then it's 5 factorial. Okay? This is going to be, all right, how many negative ones are there? There are an odd number of them, right? So that'll be negative in the end. Then you've got 2 times 2 to the 5, which is 64. Right? 5 factorial, of course you should all know, is 120.
I didn't know that.
I'm kind of joking. It's 120, and it looks to me like there's a factor of 8 that you could take out of all of this, right? Is that not obvious? Well, to be honest, I first saw a factor of 4, and then I'm like, I'll still have 2 even numbers. Yeah. So if you divide this by 8, I believe you should get minus 15, negative 15. You divide this by 8, you get that. Okay.
So can you look at this question and be like, oh, I'm gonna expect to get a factorial.
Okay. Bless you.
Bless you.
So the short answer is, now that you've seen this, yes. because recurrence relations are built on this n minus 1, n minus 2 business. Yeah? So that's what a factorial is defined as. So therefore it's like, oh, now that I see it, and you guys, you didn't need me to tell you. By the time I'd written this and then written it again, you were like, ah, cool, we have, don't you love that mathematicians have come up with, excuse me, notation to pull something like that down to something like this. Okay?
N minus 2.
If there's an n minus 2, n minus 4, etc., yeah, then you've got a bit more of a problem. And then, I mean, there's not a nice way to do that. I mean, you could involve a couple of factorials, but I probably wouldn't. I'd probably write it as, and it's not the first time, you might write it as n minus 2 times n minus 4 times n minus 6 to the dot, whatever the last term is, right? It might not be even 2. It could be 3. It could be anything. In fact, I'll refer to that in a second. Okay. Now, I'm just going to show you this, because, I mean, you can do this yourself, I suppose, but, here we go. One of the tricky things with making up questions yourself is like, so, how did I go? How did I go? So this is Wolfram Alpha. You should spend a lot of time on Wolfram Alpha. It's so amazing. I can't believe Wolfram Alpha didn't exist when I was around. So what were we integrating again? Was our last thing? I believe it was x times, I actually had, let's be a bit cheap here. I actually had log x, right? Log x. And I had that whole thing was to the power of 5. Is that right? And conveniently, I didn't even say this, but conveniently the boundaries were from 0 to 1. Okay? And when you say, hey, what do you think? What do you think? He twiddles his thumbs for a little while, and then he's like, yeah? minus 1.875. Do you want to tell me what minus 15 over 8 is? It's minus 1 and 7/8. Bam. Okay.